anything that is invested in and the work that is done, we're going to end up multiplying the set of folks that are interested. Okay, the tractor beam piece of it is just one piece of the mathematics in the engineering that we need to understand for the broader problem. Yep. The fact that you can do other wild things with that is, we want anyone that encounters this stuff to be able to look at it and say, hey, not only are they saying something interesting, I can think of something I can do with that. There's something useful for what I want to do.
And you have the map there.
Informally, how enthusiastic is NASA about repurposing this piece of ISS hardware? I mean, is it just they're not really using it?
No, that's not the case. To be frank, the principal investigator, Rich Reinhardt's first expression when he heard of this was, he said, Gary, we didn't intend it to do that. And I said, but how are we using it, Rich? He said, well, you're using it exactly as we intended. Okay, so tell me what's wrong, Rich. And he said, it's not. This actually makes sense. Okay, but the deal is that you actually have to give me an experiment opportunity proposal that meets all the requirements. Okay, so I can agree to this. Okay, it's one thing to talk about it. Okay, but you've got to be able to lay it out as an experiment that has clearly defined resource needs, that tells me exactly what you're going to do, so that I'm in a sense your first customer in terms of risk mitigation. You're going to be able to explain to me how this can be done and work. So it is not a done deal. I'm not, their committee has not signed off on this experiment, but it is being taken seriously, and it is up for approval.
Could you show again the ISS image slide where the test bed's located, please? And I don't recall you mentioning any need for battery improvement or battery usage in any of this proposal that you're talking about, is question 1. And 2, if other organizations want to be part of this effort, do they go through your existing partners, or do they contact you directly?
The right thing to do is contact XISP directly. There is unique aspects about the fact that this is coming in under the Space Act umbrella agreement approach. It offers a basically part of the deal is the Space Act umbrella agreement is unfunded, but it effectively provides an authorization to market across directorates, across centers at NASA, as well as between NASA and other government agencies, commercial entities, universities, and individuals that are of interest. And it explicitly encourages lower level funding agreements that result in the implementation. And I think one of the most telling things is the Assistant Associate Administrator for Sam Shimeni, faced with this, put it quite simply. He goes, Gary, I think you got something interesting, not only with this mission, but the other ones that we're proposing. But this is the deal. Okay, if you want my approval on this, you have to be able to provide a way for NASA to have skin in the game. We want the option of being able to, fund through the multiple, procurement vehicles that are available, the pieces of this that are of interest to us. I told him I was willing to do that. And the battery deal is that I believe that this is one of those interesting opportunities to leverage other folks' interests. In most applications of batteries, there's this notion of a trickle charger. Okay, and you have, in most energy systems, you have some form of storage, so we can be a cooperative element in that. I don't have a specific expertise in battery design or development. So it's a bit out of my ken, but I think there's opportunities for cooperation there. In the rear.
Are you familiar with the work of Lee Marable of Rensselaer Polytechnic? He's been working on this light craft now for the last 20 years, beam power. It could use this beam power to propel vehicles near in the atmosphere.
I'm not specifically familiar with his work, but there have been multiple applications that have been proposed. What I want to go off and do is find a test environment where I can do this for real, make some customers happy, meet their requirements, and get things happening.
It's 11:35.
Yeah.
I think we have
Yeah.
one more talk before lunch.
Yes. Okay, our next.
Load this
Yeah.
on. Gary, would you mind loading this? I could start
Yeah.
while you're loading it.
Sure.
I apologize that I could not make the beginning because I think what you said feeds into somewhat of what I have to say. I guess I should speak into the mic. Anyway, open up a folder called ISDC 2014 and SSP session. Anyway, I'm going to talk about phased array antennas for wireless power transmission. While Gary loads it up, I'm going to say a little bit about myself and the presentation. I have an informal but official affiliation with the Richard Lugar Center for Renewable Energy at Indiana University, Purdue University in Indianapolis, which is directed by Peter Schubert, who's on the NSS Board of Directors. Peter this was done actually on my own, not through them, but he was happy for me to use the affiliation. Actually, what I have to say today is about 2/3 congruent with a talk I gave at the 2011 ISDC in DC. Or no, that was 2012. Which in turn was about 2/3 congruent with the work I did while I was at New York University, which I presented at the Space Studies Institute conference in 1995. So I want to thank Gary Hudson of the Space Studies Institute for giving me permission to reuse and adapt the material. The PowerPoint version 5 would be the best one. So I'm going to, as soon as the charts come up, I'm going to get into phased array antennas, and it's going to be fairly mathematical but fairly elementary. That is, I'll spend 2 seconds on the equations just to show you that they exist. Now, when you talk about, let's go full screen, and when we talk about phased array. Unfortunately, it takes me 5 minutes to say the whole name of my affiliation. I am actually based in Southern California. I'm not living in Indianapolis. And in fact, I live 8 miles from here. You can almost see my house from the hotel. Phased arrays are planar arrays of dipoles or slotted waveguide elements, small antenna elements, all acting together as one. Now, by varying the current distribution to the various elements of the antenna, you can do some tricks with the beam. You can control the shape of the received beam. You can also steer the beam, although I'm not going to get into that here. For the purposes of power beaming, what you want to do is have a nice, relatively even distribution of energy out on the rectenna and minimize the side lobes, which are energy that fall outside of the main beam, which are too dilute to convert to electricity economically, but nevertheless cause interference with communications. There's an infinite number of energy distributions that can be considered, but the one I'm going to talk about is described by that, the current distribution described by that ugly-looking equation toward the bottom, which is basically even-numbered polynomials. You can forget about that as soon as I said it. All you have to know is the exponent can be 1, 2, 3, and so on. Again, there's any number of cases you can consider. The 1980 reference design had something called a 10 dB Gaussian taper, but this makes it easy to parameterize the beam taper. This is kind of a very notional design of what a phased array might look like. In practice, there are a lot more elements than that relative to the size of the array. The elements themselves are half wavelength long dipoles, spaced no more than half wavelength apart. If they're spaced more than that, you'll get something called grating lobes, which we can talk about those offline if you're interested. So by varying the current to these dipoles, you can vary the energy received at the other end, or the energy intensity, that is the power per unit time per unit area. And there are different geometrical arrangements. You can have the different columns offset from each other a little bit, or you can have, there are different shaped elements that people have constructed. But this is kind of schematically how it works. Now, the energy you get in the far field, which Gary referred to far field, so I won't belabor that concept, that basically means your rectenna is many, many, many transmitting antennas away from the transmitter, so relatively speaking. So the far field, if I shine a laser at that, to point it out, which is right here, the chart is this chart is in the far field of the laser, so it obeys geometric optics. For a rectenna, the far field might be like hundreds or thousands of, well, hundreds of kilometers for the wavelengths we're talking about for power beaming. So I'm not going to belabor that. Suffice it to say that you get an electric field. The square of that is the power per unit area. Now, the side lobes are undesirable, and I'm just showing this to quote the work of Seth at JSC, who years ago discovered what I believe he called a really good intensity pattern, which combines cases 1 and 4. And you don't have to worry about what the math actually means. The J is a Bessel function. I'm just looking at a family of cases. So the current for the different cases at the transmitter looks like this. Case 1 on top, and this is a little bit of an apples to peaches comparison. I suppose I really should have lowered number 1 because it's the same energy but distributed more evenly across the antenna. So if you transmit this current, that is, if you feed this current to the transmitter, you get this electric field at the other end, and if you want to know the energy, you square the electric field, and you get these energy intensities. So what that amounts to is case 1 is a constant, a flat distribution at the transmitter. It gives you this high peak of case 1. A somewhat broader distribution at the transmitter gives you case 2, and so on. And so basically that means you feed that upper left distribution to the transmitter to get that lower right distribution at the receiver, so that the flatter it is going in, the higher the peak at the other end. And as you make it less flat, the peak will spread out so that you have a more even distribution at the rectenna. But you don't want to spread it out too much, otherwise your rectenna is going to get bigger. And I'm going to talk about how to size a rectenna. So you have these different energy distributions across the rectenna, and these are dimensionless units. If you want to know how many meters away, well, you have to feed in wavelength and transmitter size and all that. I didn't do that for this presentation. I've done it in past work, but for this time, I'm just showing you how they relate to each other. And then later on, I'll show a little bit about how it relates to a practical problem. So this is a family. This shows the trade-offs that you want to do. You want the intensity to be as intense as allowable for safety or environmental reasons or regulatory reasons. But at the same time, you don't want it to tail off too rapidly, because the rectenna is the outer parts of the rectenna are not going to be even worth their own cost to build if the energy isn't intense. So what that means is, if you can see over here, up here you got lots of energy, but this goes way down really quickly. This one spreads it out more evenly. But there's stuff going on here that may cause interference, and I want to show you how to get rid of that. So this is case 1, the least tapered case, that is the constant energy across the face of the transmitter. And as you taper it more and more, you see that the peak goes down, but it spreads out, and you notice that the side lobes are going down. So let's see what happens to the side lobes. And for the untapered case, I blew up the side lobes and chopped off the peak and expanded the scale. Side lobes are really high, but as you taper it, it goes down. And notice that you can tell that the peak is a little more, that central lobe, that central maximum is more evenly spread across the rectenna. And in fact, the question is, do you really want to, at most, you want to build the antenna this wide? And even like out here toward the tail of the beam, it doesn't pay to build a rectenna. So let's talk about how big to make a rectenna. And you can see for case 1, relative to case 1, 84% of the energy is contained in that central maximum, but at least if you taper it, 98% or more is contained in the maxima of those other cases. And so it's a way to put more energy into that central maximum, but it does spread out. So you have to kind of do a little trade-off. And you'll notice also the relative radius of the 84% capture area relative to case 1 actually goes down for cases 2 or 3. That is to say, you're getting more energy in a smaller area if you spread the beam out wider. And it sounds paradoxical, but that's because it's a smoother distribution. So let's look at which case. Let's skip that one. Now, the way in which you might size a rectenna is you've got these different, this is the integral of the other cases. This is cumulative energy contained within a given distance from the center. So here, case 1, you see, reaches a point of diminishing returns really quickly. The other cases, you've got to build, for a given amount of power, you've got to build a bigger rectenna. But notice 2 and 1 cross over here. So let's do an exercise on how to make a rectenna. Let's say you want to capture 95% of the energy. So there's 95% capture, and then let's read down where those numbers are. And case 1, you can't even do it. So it does pay to taper the beam. Case 2, it's a relative size of 3.8. What Dr. Seth computed as a good case is 3.9. Actually, with some round-off error, it's almost the same. And then for more tapered cases, the beam spreads out even wider. I looked at case 2 and what he called the good case, and the central maximum is almost the same. So I thought, what's the difference between the good case, which is 1 plus 4, and number 2? I looked at the side lobes, and I see what he was doing. The case 2 has this one really big side lobe, but the Seth's special case has really low side lobes, though after about this point, it kind of doesn't matter. So he had a way of getting rid of this side lobe, and some of the energy goes into the main lobe. And when I looked at this, I thought, what if we combined the good case with case 2 out of phase and canceled them? Then all of the energy would go into this side lobe, and virtually none would be in the main lobe. It would cancel out. And so the peak would be off-center if you combine them. But this is, imagine this revolving around the axis. So in 3 dimensions, it looks like this, which means the beam would actually be hollow. It would be null at bore site. I have since had some doubts about whether or not in practical phased array you can really implement this as shown. The math works out because of superposition. And in order to make sure half of you leave to go to lunch, I'll make a bad mathematical statement. I believe this works because of the linearity of the Fourier-Bessel transform. You're still here. I'm going to continue. However, I admit that as Gary quoted, in theory, there's no difference between theory and practice, and in practice there is. So where my doubts about my own work lie is, can you actually implement it on an actual phased array? Perhaps we can launch some CubeSats and find out. So we got to talk. Now, I also had the idea that if these two are so similar in the middle and so different off to the side, that can you encode digital information, and the central maximum where you're beaming the power is virtually unaffected, but the side lobes are so different that you're switching between a 1 and 0 in this region, and you're transmitting information in the side lobes, and the main lobe where your rectenna is does not care, and your side lobes where you might have some receiving antennas to receive uplink information for, say, a space-to-space, does care. Again, in theory, the math works. In practice, I wanted to implement this as the uplink for an actual geo-solar power satellite. I've since come to doing some more math, which is not difficult, but I'll spare you anyway. The limitation on communication is the size of the antenna. The antenna must communicate with itself. The period of a signal going from one side of an antenna to another is going to limit the comm bandwidth. So I have some doubts about whether side lobe modulation, as I call it, will work for a geosat. I think it will work for the scale of experiments that Gary has proposed. I think we can transmit information and power in the same beam. And so I sort of brainstormed with myself on applications for the hollow beam. I had the idea of beaming power to a crater on the moon where you don't want any of the energy to fall in the middle. And somebody mentioned Lake Mirabel's light craft. 2 or 3 versions ago of this, I showed this at the Princeton conference. Lake was there. He said, oh, this is what I need for my light craft, a hollow beam. He referenced my paper in his paper in the same Princeton proceedings that the earlier version of this. So I think the hollow beam may have practical applications for the light craft. And again, I'm kind of more sanguine about smaller scale applications. His laser light craft is about yay big. His human rated capsule, I think, is about dragon size, I believe, if anybody's read up on his work. So I think that could work. But again, we got some opportunities in the near term to test how theory differs from practice. And I think the smaller scale will work better. But nevertheless, I've also thought of, say, COM and NAV to rims of things like coastlines where most people live. You can have a nadir pointing antenna, and the people at whatever is at nadir, I thought of put a satellite in the mid-Pacific where there's not too many satellites, lots of geo slots available, and then beam COM. I don't think it would work for power, but COM to the Pacific Rim. That might be a little challenging because the Pacific Ocean is really wide and the elevation angle of the satellite would be pretty low. It might work in smaller geographic areas. Most people live on coastlines. The demand for COM and NAV is near coastlines. So I would propose this in theory as a way to augment GPS or COM in areas of high demand for bandwidth and precise nav and direct the energy where you want it. And so in conclusions, a phased array basically is a bunch of antennas acting together. Where it differs from Gary's work is they are physically bolted to the same structure, but Gary showed you some free-flying applications, and I've done some work on free-flying co-orbiting formation-flying satellites in my former employer. That comes in the early part of the alphabet, and and I'm not sure well, it's a patent pending actually for an idea we came up with, and I've never actually combined that with power beaming, but let's talk. The side lobes of a power beam can be reduced at the expense of broadening the main lobe. And the cases studied here is particularly useful, and they can combine in innovative ways. And just to show you briefly some real-world numbers, you'll notice at the end I did do this calculation for the taper for a 5 gigawatt SPS, and for not tapering it, 811 megawatts are in the side lobes. That's a lot of waste. Even a little bit of a taper reduces that by about a factor of 9. So a certain amount of beam tapering is worthwhile, but if you overdo it, the central maximum is going to be spread a little too thin. But now that you've seen this family of curves, those of you who are as masochistic as I am can go and combine them in different ways and can create a virtually unlimited number of beam shapes. So my closing thought is thank you for all these people who laid the groundwork. I see 2 of them are me, but Peter Glazer, and now I see that Gary and others are building on that. So I think we're almost time for lunch, but do we have time for a question?
Yes, we're good up until...
Okay, yes, Keith.
How much beam sweep can you easily get out of a phased array antenna?
Yeah, I would say that's about right. You configure cosine loss, which would be, I guess, about a 70% factor at 45 degrees. You can get 45 degrees. There is a beam sweep loss in gain. There's 2 things going on. There's a loss in gain, and because of effects of the dipole has its own pattern, and there's the cosine loss. The cosine loss can be engineered around by sizing and powering your array. The scanning loss cannot.
A big
A big long oval would be practical. I would guess about 45 degrees would be about either way.
Only 1.4 square root too.
Yeah. I would say at least 45. You could probably, I used to play with numbers like around 55 because you cover, you know, the United States and most of the populated areas of Canada with beamed power.
The reason I'm interested, this is a really recent interest.
Yeah.
This I'll go into the talk tomorrow, but we figured out a way to build and move then a laser power, a laser, propulsion laser source from LEO out to GEO. Since we have to provide power anyway, we figured we'd use electric propulsion to get it out there.
Yeah.
But to get it out, you don't have very much view time of it initially. Still, it only takes 30 days to get it out there, 28 actually.
I did a paper on that at an earlier ISDC. If you can find it, I don't even know if I have it anymore, but let's talk offline.
Okay.
Yeah.
It turns out that beam steering is pretty critical. You have to stick it right on the equator.
Yeah.
It's a way to reduce the cost from a factor of 2.5 to maybe 1.5.
My work was a LEO orbiting power beamer in a polar orbit.
No, this is on the ground.
Okay.
Taking power up to the space vehicle.
Yeah. I hadn't considered that. I think there's probably, yeah, actually, I did consider it. When I was at NYU. We were actually researching space-to-Earth power beaming before we got into SPS. We actually had a picket fence of transmitters around the Arctic Circle beaming to some SDI satellites that needed a lot of power. I think it's been looked into before. I think it can be done. I don't know. I can't exactly answer your question, yes or no. I think it's worth considering. We have time for one more? Well, one more, yes.
Real quick, did you, what were your assumptions on distance? Was this geostationary orbit, or was this from anywhere?
It was purely, as long as it's in the far field, which you are almost always going to be. Now, Gary talked about near field work, which I hadn't looked into. That's going to involve some more like brute force ray tracing kind of computation. But this is assuming far field, and I forgot the exact formula, but it's a certain number of antennas away from the antenna. That was the only assumption necessary. It will, and as far as the actual, those numbers I showed, that's based on GEO, yes. That's based on 5 gigawatts from GEO. Yes. I guess that's all that we have time for. Thank you.
Thank you very much.
And I guess I'll let you eject.
Okay, ladies and gentlemen, we'll be pulling things back together at 2 o'clock. I'll enjoy lunch.
I'm going to follow the crowd. Probably in California. Oh, thank you.